a beautiful day outside? Perfect for a stroll. Oh look, what's this? It seems to be a fossil. Did you know that isotopes can be used to date fossils? I wonder how old isotopes are. Let's go to Juhi for more information.
Isotopes were first discovered through a series of experiments by Dr. J.J. Thomson and his associate F.W. Ashton. Through their experiments, the two showed that when some substances are ionized, they prove to have species which are much more heavier than the original content. Speaking of Dr. J.J. Thomson, there he is. The term isotopes comes from a combination of two Greek words, isos, meaning equals, and topos, meaning place, gives you the word isotopes.
Nuclei, the protons and neutrons at the centers of atoms. We call them nucleons. Protons define the element, its chemistry. Neutron numbers affect elements with subtlety. They define the isotopes, and with effort they hope to make some that no one's ever seen before, and that's dope. So you know the elements from the periodic table, but this other version highlights isotopes that are stable. The isotopes we know are on a diagonal track, and at first glance, I thought it looked pretty whack, but as you get away from that stable nucleus line, there's radioactive isotopes we don't usually find on Earth, because these nuclei prefer to decay into more stable isotopes by tossing particles away.
Before the discovery of isotopes, it was always assumed that the mass of the standard numbers of atoms in a chemical element was the most basic feature of the density. Isotopes are basically when there are variations of the same element, in which the number of protons is the same, but the number of neutrons varies. For example, on a periodic table, you see oxygen written as NO 16, and okay, the 8 shows the number of protons. The 16 shows the atomic mass. Since there are 8 protons, and this shows you that there are 8 neutrons. Okay, a variation of this can be, or an isotope of this can be oxygen 17. The number of protons is the same, so it shows you that it's the same element. Since the atomic mass is different, it shows you that there's one more neutron than there are in oxygen 16. Okay, the way these are written, this one would be written oxygen 16, and then this one would be written as oxygen 17.
Hydrogen, helium, lithium, beryllium, boron, nitrogen? Oh, carbon. I always messed that one up. Dear Tim and Moby, how can two atoms of the same element have different numbers of neutrons? From Gabriella. Whoa, good thing we've got the periodic table of elements handy. Let's look at an element as it's represented on the table. How about, say, chlorine? Cl is the symbol for chlorine. That number above the symbol is the atomic number for chlorine. The atomic number of an element tells you how many protons are in each atom. Every single atom of chlorine in the universe has 17 protons in its nucleus. The nucleus, as you should remember, Moby, is the cluster of particles at the center of the atom. It's made of particles called protons and neutrons. This number is the atomic mass for chlorine, and it tells you how heavy chlorine atoms are compared with atoms of other elements. Atomic mass is measured in atomic mass units, or U, so chlorine's atomic mass is 35.453 U. Well, the atomic mass you see on the periodic table is actually just an average mass. Not all atoms of a given element have the same atomic mass. So every chlorine atom has 17 protons no matter what, but the number of neutrons can vary. Some chlorine atoms have 18 or even 20 neutrons. Isotopes are atoms of the same element with different numbers of neutrons. An isotope is called by its mass number, the number of protons plus the number of neutrons in its nucleus. There are 2 naturally occurring isotopes of chlorine. Chlorine-35 has 17 protons and 18 neutrons. Chlorine-37 also has 17 protons, but it has 20 neutrons. About 75% of chlorine atoms are Cl35, and about 25% are Cl37. Chlorine-37 is heavier than chlorine-35 because it has those 2 extra neutrons. So there you go, isotopes in a nutshell. Don't I get a break yet? Hydrogen, helium, lithium, beryllium, boron, carbon.
Thank you, Juhi, for the information on the history of the isotope. And thank you, J.J. Thompson, for the discovery of the isotope. But I wonder, how can isotopes be used in the real world? Let's go to Jessica for more information on how isotopes can be used. Oh, hey! Didn't see you there. Well, to answer Luna's questions, there are several important ways that isotopes are used in medicine, such as bone imaging or treatment of cancer. Diagnostic techniques use radioactive tracers, which emit gamma rays from within the body. These tracers are generally short-lived isotopes that link to special chemical compounds. They can be given by injection, inhalation, or taken orally. The second type is a more recent discovery. It's called positron emission tomography, also known as PET scan, which a lot of you may know. And oh look, it's a picture! See, this is the PET scan. Okay, well basically what the process is, a positron-emitting radionuclide is introduced by injection, and this accumulates in the target tissue. As it decays, it emits a positron, and this positron quickly combines with electron and two identifiable gamma rays, and these emit in the opposite direction from each other. So the PET camera detects these. This development is really important in oncology. It's the most accurate, non-invasive method of detecting and evaluating most cancers. And as you can see, this is a PET scan of a human brain.
For basic science, effort could hold answers. For medicine, specifically the treatment of cancer, isotope therapy shoots nuclei into tumors, killing cancer cells to keep the patient out of the tomb. The beam packs the most punch in the place where it halts. Since it stops in the tumor, it overcomes the faults of ordinary radiation, traveling all the way through, so isotopes have fewer side effects than X-rays do. Targeted radiotherapy is also under study. Inject an isotope into the patient's body, attached to a carrier that brings it into the tumor, where it decays, killing just cancerous tissue.
So, in short, these methods provide a view of the position and the concentration of the radioisotope in the body. Organ malfunction is detected if the isotope is partially taken up in the organ or taken up in access. Also, an unusual pattern of the isotope movement could indicate malfunction or the isotope rate. Did you know that 10,000 hospitals worldwide use radioisotopes in medicine? Isotopes are really useful. Wow, thanks for that information, Jessica. I didn't know any of that. I wonder if there are any more common day-to-day uses. Let's go to Ashika for more information.
Well, Luna, there are many uses of isotopes. How many of you have smoke detectors in your households? Chances are that most of you do. What many people don't know is that these small units contain a bit of americium-241. Their radioactive properties can be used to detect smoke from a fire at a very early stage. 80% of all household accidents involving fires occur in households without smoke detectors. On a broader aspect, isotopes can help understand the chemical and biological processes in plants through a Geiger counter. Remember when Luna found this fossil? Carbon-14 dating can be used to determine its half-life and when it died. Oh look, here are another two examples. Now you guys have learned a lot about isotopes. Let's go back to Luna.
Thanks for all that information, guys. Now that you've learned much more about isotopes, I'm sure that you can understand that isotopes are found everywhere in the world. From common uses in smoke detectors and other household objects to broader uses in the scientific world. We can understand that isotopes are found just about everywhere. Here's a quick recap, and thank you for watching.